PPT ഉണ്ടല്ലോ. So the last class we discussed about the relationship between the shear stress developed across a member subjected to torsion and the applied torque. Okay. So based on this figure, first we derive a relationship between the modulus of rigidity and shear stress, that is tau by r equal to g theta by L. Tau by r equal to g theta by L. That was the first relationship developed just by considering these two. Here we have an r, b dash, and this angle is theta. This angle is shear strain gamma. So by the arc length is equal to r theta. So here it is L, and this is r. So from this diagram, we derive this relationship tau by r equal to g theta by L. Then in last class we draw a cross section. In that cross section, I take a small element that is at a distance x from the center, and in that element a shear force is developed. We calculate the shear force acting at that element, that is equal to the shear force F is equal to tau 2 pi by r into tau into x square into dx. X square into dx. That was the shear force developed in this small element. Okay, and this shear force make a moment with respect to center. So moment is equal to force into perpendicular distance. Here the perpendicular distance is x. This distance is x. So the moment is equal to moment of F about center equal to this value into F into x. That is equal to 2 pi by r into tau into x cube into dx. X cube into dx. Okay. So that is the moment of the force F about the center. Then similarly, here we only consider this area, and in that a shear force is developed. Similarly, we have such a number of shear force. Everywhere we can see such a shear force in this cross-section area. Okay. So the totality of moment of all the forces about the center. Okay, here we only calculate the moment of single force about the center. That is equal to 2 pi by r into tau into x cube into dx. So the moment of all the forces about the center, for that we integrate. So that we integrate. So totality of or total moment of all forces, all shear forces about the center equal to integral the center mudal surface variant. That means 0 to r. Center mudal surface variant, the range is 0 to r. 2 pi by r into tau into x cube into dx. Integrate ചെയ്യുമ്പോൾ ഈ ഫോഴ്സസിന്റെ എല്ലാം with respect to center ഉള്ള total moment കിട്ടും. So that is equal to, here these terms are constant. So we take outside 2 pi by r into tau into integral 0 to r x cube dx. That is equal to 2 pi by r into tau into x cube into integral, that is x raised to 4 by 4 in the range of 0 to r. That is equal to 2 pi by r into tau into, here we apply the range. So r raised to 4 by 4 minus 0 is raised to 4 by 4. So here r raised to 4 by 4. I'm converting this r with the d. So it is equal to 2 pi by r into tau into Here R is d by 2. D by 2 whole raised to 4 by 4. Okay, so this is equal to 2 pi by R into tau into d raised to 4. 2 raised to 4 is equal to 2 into 2, 4, 8, 64, 64, 64. So this is equal to pi by R into, tau by R into, this is equal to tau by R into pi d raised to 4 by 32. This is the total moment of the cross section. There are different shear forces developed across the cross section because of the external torque. The moment of all the shear force about the center is equal to this value, tau by R into pi d raised to 4. And what is this shear force? What is this shear force or moment of this shear force? That is the what we explained yesterday. That is this moment of all the shear force about the center is the resistance offered by the cross section against external torque. So the resistance torque offered by the cross section about the external torque is equal to this total moment. So this developing all forces about the center developing moment the total resistance torque. Total resistance torque. So we can write this is equal to, and the resistance torque equal to applied torque. Okay, so we can write this is equal to T. This is equal to T. So we can write the torque T is equal to tau by R into pi d raised to 4 by 32. We got a relationship between tau and T. Applied torque is equal to shear stress developed across the cross section and all other factors. Okay, so this is the equation. T is equal to tau by R into pi d raised to 4 by 32. In this equation, this T is equal to tau by R into this pi d raised to 4 by 32 can be called as polar moment of inertia. Polar moment of inertia. Tau by R into J. We represent pi d raised to 4 by 32 as J. Okay. So from this we got T by J equal to tau by R. This is equation number B. T by J is equal to tau by R. So we got T by J is equal to tau by R. And coming to the equation number 1. So equation number B was T by J is equal to tau by R. That is equation number B. And this is equation number A. Tau by R equal to G theta by L. So here the right hand side and left hand side are same. So we can combine these two equations. That is equal to T by J is equal to tau by R equal to G theta by L. This is an equation of designing a body subject to torsion. T by J is equal to tau by R equal to G theta by L. Any doubt in this portion? Any doubt? Yes. Yes. Circular shaft in the design of it. Shaft in the design. നമ്മൾ ആക്ച്വലി ടോർഷണൽ ബോഡീസിലെ ഷാഫ്റ്റ് ഡിസൈൻ ചെയ്യുന്നുള്ളൂ. മറ്റേ ഇത് ചെയ്യുമ്പോൾ നമ്മളെ ഇന്റഗ്രേഷന്റെ റേഞ്ച് മാറിപ്പോകും. ഇന്റഗ്രേഷൻ വേറെ പ്രൊസീജിയർ, ഡെറിവേഷൻ വേറെ. ദിസ് ഇസ് ഫോർ എ ബോഡി സർക്കുലർ ക്രോസ് സെക്ഷണൽ ബോഡി. ഓക്കെ, കാരണം ഇവിടെ യൂസ് ചെയ്യുന്ന ജെ ഒക്കെയും സർക്കുലർ ക്രോസ് സെക്ഷൻ പൈ ഡി റേസ് 4/32. സോ ദിസ് ഈസ് ഫോർ എ സർക്കുലർ ഷാഫ്റ്റ്. ഹൗ ടു ഡിസൈൻ എ circular shaft subject to torsion. T by J is equal to tau by R equal to G theta by L. What are the different components here? T is torque. Torque. നമ്മൾ ഒരു ബോഡിയിൽ അപ്ലൈ ചെയ്യുന്ന torque. External torque is T. External torque is T. What is J? J is called polar moment of inertia. Polar moment of inertia. I will explain what is that. Inertia. Tau. Tau is the, if we take any cross section, in that cross section, so I am taking a cross section here. This is my cross section. In that cross section, I take a small element here. A small element here. Okay. So in this shaft, I take a cross section. This is the front view of that cross section. In that, I take a element. And that element is at a distance r from the center. That element is at a distance r from the center. This r is this one. Okay, this er and all. That is the distance from the center to element which we are considering at the cross section. That is this r. And in this r, a shear stress is developed. That is tau. In this element, a shear stress will be developed. That is tau. So in this tau by r, we have an element at the cross section. The distance from the center to that element is r. This is very important. This r is not the radius of the shaft. It is the distance from the center to the element which we are considering to calculate this tau. Okay. So this r is the distance from the center to the elements which we are considering to calculate this tau value. Okay. In this element, the tau value is active. That is at a distance r from the center. And G is the material property, that is the shear modulus or rigidity. It will vary with respect to the material. For steel, it has a G value. For aluminum, it has another G value. So it is a material property. And theta is the angular twist. How this after applying torque, how much a point twisted across the cross section. That is angular twist. L is the length of the shaft. These are the components of this equation. Okay. Any doubt in this? Yes. അതായത് നമ്മളൊരു ഷാഫ്റ്റ് എടുക്കുമ്പോൾ ആ ഷാഫ്റ്റില് ഏത് പോയിന്റിലാണ് ഷിയർ സ്ട്രെസ് മാക്സിമം എന്ന് അറിയണ്ടേ, അല്ലെങ്കിൽ ഏത് പോയിന്റിലാണ് ഷിയർ സ്ട്രെസ് മിനിമം എന്ന് അറിയണ്ടേ? ആ എലമെന്റ് ഇപ്പൊ എനിക്ക് സെന്ററിലെ ഷിയർ സ്ട്രെസ്, ഒരു ക്രോസ് സെക്ഷന്റെ സെന്ററിലെ ഷിയർ സ്ട്രെസ് കാൽക്കുലേറ്റ് ചെയ്യേണ്ടത്. അപ്പൊ നമ്മൾ R0 എടുക്കും. ഒരു ക്രോസ് സെക്ഷന്റെ ഔട്ടർ സർഫസിലെ ഷിയർ സ്ട്രെസ് എടുക്കണ്ടെങ്കിൽ R എന്ന് പറഞ്ഞ ആ ക്രോസ് സെക്ഷന് റേഡിയസ് എടുക്കും. ഓക്കെ, അങ്ങനെ നമ്മള് ഒരു ക്രോസ് സെക്ഷനിൽ എങ്ങനെയാണ് ടോ വേരി ചെയ്യുന്നതെന്ന് കാണിക്കാനാണ് ഈ ടോ ബൈ ആർ യൂസ് ചെയ്യുന്നത്. ടോ ബൈ ആർ. ഇനി ഇതില് ഒരു ഇമ്പോർട്ടന്റ് ടേം ഉണ്ട്, പോളാർ മൊമെന്റ് ഓഫ് ഇനേഷ്യ. Polar moment of inertia. What is moment of inertia? Or have you studied?
Resistance offered for rotation.
Okay. Resistance offered by against. We call the term inertia. That is the resistance offered by a body against changing its uniform speed or changing from the rest position. Okay. So, our change in inertia എന്ന് പറഞ്ഞ term use ചെയ്യുന്നത്. And moment of inertia, that is nothing but it is the resistance offered against rotation. Okay. So this polar moment of inertia is specifically for a body subjected to torsion. Body subjected to torsion. That means a body with a particular cross section. A body with a particular cross section offer a resistance against torsion. The torsion is actually a type of rotation, right? A torsion is actually a type of rotation. This is actually rotating. Okay, it's a type of rotation. But more specifically, we give a polar moment of inertia value for such type of rotation. Okay, so for a body subjected to torsion, how this body, how this cross section, it is a cross sectional property. Okay, the molar moment of inertia for a circular cross section, that is equal to pi d raised to 4 by 32. Or if it is a rectangular cross section, it has another value. So it is a cross sectional property. So by varying the cross section, how much this body offer a resistance against the torsion. Okay, so the resistance offered by a cross section of a body against torsion is represented by this polar moment of inertia. Okay, okay, that is polar moment of inertia. And we have area moment of inertia, mass moment of inertia. So what is area moment of inertia? Area moment of inertia. കേട്ടിട്ടുണ്ടോ നിങ്ങള് മെക്കാനിക്സ് സോളിഡ്സ് പഠിച്ചല്ലേ ഏരിയ മൊമെന്റ് ഓഫ് ഇനേഷ്യ മാസ് മൊമെന്റ് ഓഫ് ഇനേഷ്യ എന്താ കേട്ടില്ല
ഇന്റഗ്രൽ വൈഡ്
that is the formula. What is the definition of area moment of inertia? നിങ്ങൾ ഒരു ഞാൻ പറയാം ഒരു എക്സാമ്പിൾ ഞാൻ പറയാം ഫോർ എക്സാമ്പിൾ സോഫ് ചെയ്തിട്ട് ഓൺ ആക്കി കേട്ടോ നമുക്ക് just a second. Okay, so for example, so for example, you take a wooden rod. You take a wooden rod, and you are trying to rotate this rod by holding your hand at the center. That means like this. ഇതുപോലെ ഒരു wooden rod എടുത്ത് സെന്ററിൽ വെച്ചിട്ട് നിങ്ങൾ റൊട്ടേറ്റ് ചെയ്യാണ്. Okay, ഇങ്ങനെ റൊട്ടേറ്റ് ചെയ്യാണ്. It will be very easy to rotate that heavy wooden rod. Okay, when we support at the center, when we give the support at the center and try to rotate this wooden rod, it will be very easy for the rotation of this wooden rod. Okay, but if we hold this wooden rod at this end, and if you try to rotate like this, it will be very difficult. നിങ്ങൾ ഇതുപോലെ എക്സ്പീരിയൻസ് ചെയ്തിട്ടുണ്ടോ ഒരു ഹൈ മാസ് ഉള്ള ഒരു ബോഡി സെന്ററിൽ നിങ്ങൾ റൊട്ടേറ്റ് ചെയ്യുമ്പോൾ ഇറ്റ് വിൽ ബി വെരി ഈസി ഇതുപോലെ സെന്ററിൽ ഹോൾഡ് ചെയ്തിട്ട് റൊട്ടേറ്റ് ചെയ്യുമ്പോൾ ഇറ്റ് വിൽ ബി വെരി ഈസി ബട്ട് ഒരു മാസ് ഉള്ള ബോഡി ഈ ഒരു എൻഡിൽ പിടിച്ചിട്ട് റൊട്ടേറ്റ് ചെയ്യുമ്പോൾ ഇറ്റ് വിൽ ബി വെരി ഡിഫിക്കൽട്ട് നിങ്ങൾ അത് എക്സ്പീരിയൻസ് ചെയ്യണ്ടോ അങ്ങനെ ഹലോ കേൾക്കാമോ
യെസ് സർ അങ്ങനെ എക്സ്പീരിയൻസ് ചെയ്തിട്ടുണ്ട്
ഓക്കെ സോ നിങ്ങൾ അല്ലെങ്കിൽ നിങ്ങൾ വീട്ടിലൊരു ഒരു മരത്തിന്റെ പലക എടുത്തിട്ട് സെന്ററിൽ ഇതുപോലെ പിടിച്ചിട്ട് റൊട്ടേറ്റ് ചെയ്യാം ഇങ്ങനെ റൊട്ടേറ്റ് ചെയ്യുമ്പോൾ ഈസി ആയിട്ട് നിങ്ങൾക്ക് റൊട്ടേറ്റ് ചെയ്യാൻ പറ്റും പക്ഷെ ഈ എൻഡിലോ അല്ലെങ്കിൽ ഓപ്പോസിറ്റ് എൻഡിൽ വെച്ചിട്ട് റൊട്ടേറ്റ് ചെയ്യുമ്പോൾ ഇറ്റ് വിൽ ബി വെരി ഡിഫിക്കൽട്ട് ഓക്കെ അത് നിങ്ങൾക്ക് വേണമെങ്കിൽ ഒന്ന് ചെക്ക് ചെയ്ത് നോക്കാം സോ വാട്ട് ഈസ് ദ റീസൺ ഫോർ ദാറ്റ് the mass is same here the mass is same here also the mass is same but when I change the position of rotation I feel difficult to rotate the rod. What is the reason?
The distribution of area around centroid on either side is different as we move along the centroid. അപ്പോൾ അതിനനുസരിച്ച് ഇത് കൂടില്ല ഏരിയ മൊമെന്റ് ഓഫ് ഇനർഷ്യ കൂടും
ഓക്കെ രണ്ടുപേരും പറഞ്ഞ കറക്റ്റ് ആണ് ഏരിയ അല്ല മാസ് ആണ് ഇവിടെ അല്ലെ ഹിയർ വി ടേക്ക് ദ മാസ് ഓക്കെ mass moment of inertia is different in these two cases. In both cases mass is same but the mass moment of inertia is different. What is the reason? Here if we hold this rod at the center the mass is uniformly distributed. Here we can say this is m by 2. At the in this end, in the right end, we have m by 2. So mass is uniformly distributed across the rotation axis. This is my rotation axis. Okay, this is my rotation axis. So the mass is uniformly distributed here. But here in this case, this is my rotation axis. Entire mass is distributed to the right of this rotation axis. Okay, or we can say in this case, the mass moment of inertia is very large. This mass moment of inertia is very large in this case, but here the mass moment of inertia is small. Here the mass moment of inertia is very small. Or we can say the resistance offered by the mass against the rotation in this case is very large. The resistance offered by this mass against the rotation is very easy in this case. Okay, that is mass moment of inertia. And in this mass moment of inertia, we can use the formula mk square. Okay, so in both cases, m is same, mass is same, but this k, that is different. This k is different in both cases. In this case, the k is the distance from the center of axis to the center of mass. This is the value of k. But in this case, this is the center of mass is this one. So this will be the distance for k, the center of mass to the center of axis, that is radius of gyration, that is smaller one. So if the center of mass and the center of rotations coincide, then it will be very easy to rotate like this case. So we have to make a structure such that center of mass and center of rotation should be at very small distance. Then we can easily rotate that structure. And if the center of mass and center of rotation axis, this is my center of rotation axis, if it is at a very large distance, then it will be very difficult to rotate because the mass moment of inertia is very large for that case. Okay, so this is that case of mass moment of inertia. Another one is area moment of inertia. Okay, and you may see different types of beams. For example, you may see in your truss works, you can see a T-shaped beams. Okay, the cross section is like a T. It's like a T. The beams T-shaped. Truss work T-shaped beams or I-shaped beams. We can see I-shaped beam. The cross section is like an I shape. Okay, this is the I-shaped beam. Or we can see rectangular shaped beams. Rectangular shaped beam also you can see in your truss works. Difficult bending. Which one has the difficult bending? If the mass and area of cross section is same for I and T and rectangular cross section, area cross section is same, then which one offer more resistance against bending like this? So bending and difficulty higher. Any cross section high bending resistance offer here.
Area moment of
inertia. The cross section area is same. For 3 case, the cross section area is same. Okay. So B, D, cross section area calculated in same angle, which one offer more resistance?
I section
offer more resistance. What is the reason? I section offer more resistance. The reason is the area moment of inertia for the I section is very high. Area moment of inertia for the I section is very higher than that of this rectangular as well as T section. So the area moment of inertia gives the resistance offered by a beam or a deflecting structure against bending. Okay, the resistance offered by a member or a structure against bending is called, that is a cross-section property. The resistance offered by a cross-section, it is more specific. the resistance offered by a cross section against bending is called area moment of inertia. So when we take different cross sections, in this the I section offer more resistance against the bending. So it is very difficult to bend a cross section with the I beam. Okay, it is very difficult to bend. So this cross section offer more resistance than this two. So we can say the area moment of inertia of this cross section is very high, higher than that of these two cross sections. You will study about this in the next module of beam. Okay, so that is about area moment of inertia. What is the reason for this? Here, in case of bending, this is the neutral axis. The axis passing through the neutral of the, you will study in detail about that. I am not going to explain about this. So this is the neutral axis. And if the area more away from the neutral axis, then the area moment of inertia will be high. Okay, more area concentrated away from the neutral axis. Here we can see this is the neutral axis, and in the neutral axis we have very small area, but away from the neutral axis we have a huge amount of area. So in this type of cross section offer more resistance against bending. But here we can see if this is cross section area, here we have same area that of the end portion. So this offer low resistance against bending. So you will study in detail about the area moment of inertia when we discuss about beams. So that is about area moment of inertia, and our discussion is polar moment of inertia. Polar moment of inertia. Polar moment of inertia is nothing but it is the resistance offered by a structure or member against rotation. Against rotation. Sorry, against, it's not rotation, against torsion. Okay, a member offer a resistance against torsion. So a member with a higher value of polar moment of inertia offer more resistance against torsion. So we have to select a cross section of member such that the polar moment of inertia should be very high. So that is the third moment of inertia, polar moment of inertia. So these three terms, mass moment of inertia, area moment of inertia, and polar moment of inertia is very important in case of mechanics of solid. These questions may ask in different interviews. So mass moment of inertia actually that is dependent upon the rotation of distribution of mass. So this is the resistance offered by a mass against rotation, and this is resistance offered by an area against bending, and this is the resistance offered by a cross section against torsion. So that is polar moment of inertia J. Okay. So we got two equation. We got this equation: T by J is equal to tau by R equal to G theta by L. T by J equal to, this is our designing equation. Based on this equation, we can design a shaft subject to torsion, G theta by L. Okay. In this equation, this can be divided into two. That is, T by J is equal to, T is actually the external influence or external effect. Yeah, we cannot omit this T value. So T by J is equal to tau by R. This is called strength equation. Strength equation. And another one is, we can, I separate this equation to two equations. T by J is equal to G theta by L. This is called stiffness equation. Stiffness equation. Okay. So if you want to design a shaft based on the strength criteria, that means the shaft can deflect, or there is no requirement of rotation, or it can deform, but it should not fail by fracture. That is a strength equation or strength criteria. So it can deform. That is not a problem. Okay, the deformation type of failure is not a problem. Then you can use T by J is equal to tau by R equation. That is a strength equation. And next one, the severe deformation is the main criteria. The deformation should not allow, but it can fracture. Then we have to use stiffness equation. Okay. And if you want to design a shaft with a strength as well as stiffness criteria, a shaft A shaft which should not deform in a severe manner, as well as there should not be any crack in the shaft or fracture in the shaft, then we have to use this equation, a combined equation. So we can split into this strength equation as well as stiffness equation for this equation of torsion. Any doubt? Any doubt regarding the polar moment of inertia or about this equation? Yes. Stiffness of. രണ്ടും വരാതിരിക്കാനേ നോക്കുള്ളൂ. പക്ഷെ ചില കേസിൽ ഇപ്പോ മേ ബി ഒരു അലൗബിൾ സ്റ്റിഫ്നെസ് ഒക്കെ ഉണ്ടാവും, അതായത് അലൗബിൾ ഡിഫോർമേഷൻ ഉണ്ടാവും. ഇത്ര എമൗണ്ട് ഡിഫോം ചെയ്താലും കുഴപ്പമുണ്ടാവില്ല. ആക്ച്വലി നമ്മൾ ചെയ്യേണ്ടത് ഈ സ്ട്രെങ്ത്തും സ്റ്റിഫ്നെസ് കമ്പൈൻഡ് ചെയ്ത് വെച്ചിട്ടാണ് ഡിസൈൻ ചെയ്യേണ്ടത്. എന്താണെങ്കിൽ ബോത്ത് ക്രൈറ്റീരിയ സാറ്റിസ്ഫൈ ഉള്ളൂ. In any case, strength deformation is not a factor, or stiffness or twisting is not a factor. Then we can design based on this equation. Okay, actually, it's dependent upon the problem, type of problem or type of application. But commonly we use this equation for the design of shaft. Okay. Next, I am going to design or develop this formula for a hollow shaft. In case of hollow shaft, we have a cross section like this. Okay, this is a cross section of a shaft with a hollow structure. This area, this hatched area, shaded area is filled with the material. This area is hollow. Okay, that is hollow shaft. In this hollow shaft, the center, this hollow region radius is small r, and this outer surface radius is capital R for a hollow shaft. In the same, similar to the similar to the previous case, I take a small elemental area here, that is at a distance x from the center. Arrow unmute ചെയ്തിട്ടുണ്ടല്ലോ. That is at a distance, the cross section is dx. Okay, this is rather okay. Tejas Mahadev.
Sorry, sir.
Okay. So this is similar to the solid shaft. The only difference, we have a small r and a capital R. Okay. And in this derivation, the entire thing is similar to the derivation of solid shaft, but the only difference is we have a small r in this problem. Okay. So here we have in this dx, that means elemental area, what is the shear stress? Similar to the previous case, tau x equal to maximal shear stress, tau x by x equal to maximum shear stress by small r or capital R. Which one is? Small r or capital R. Where is the location of maximum shear stress? Capital R. Okay, capital R. So tau x equal to tau by r into x. Okay. Then from this we can calculate the shear force. Shear force is equal to shear stress into area. That is equal to shear force is equal to tau x into area. That is equal to tau x into what is the area of the elemental portion? That is equal to perimeter 2 pi x into the thickness is equal to dx. So from this we got tau by r into 2 pi x square into element area 2 pi x into dx. Is right? So 2 pi x into dx, and instead of tau x is equal to tau by r into x. So x square, we got an x square. Okay, we replace tau x with a tau by r into x. So tau by r into 2 pi x square dx. We got the turning force. So the turning force acting on the elemental area or shear force acting on the elemental area is equal to this much. And again, the turning moment produced by that force, F force, is equal to tau by r into 2 pi x square into dx into perpendicular distance. Force into perpendicular distance is equal to the force into perpendicular distance again x. Okay, that is equal to tau by r into, similar to the previous derivation. There is no difference here. The only difference is the small r replaced by capital R. That is the only difference. 2 pi into x cube into dx. Okay, the total moment is equal to integral 0 to small r or capital R. Sorry, integral. What is the range? Small r to capital R. In the previous derivation, it was from 0 to small r. But here we can see the range of material is from here to here material starting. So r to capital R. Okay. So here the range is r to small r to capital R. Tau by r into 2 pi into x cube into dx. Okay. So after simplification, here x cube is x raised to 4 by this is equal to x raised to 4 by 4 in the range of r to capital R. Okay. This simplify ചെയ്യുമ്പോൾ നമുക്ക് കിട്ടുന്ന ഇക്വേഷൻ ഇതുപോലെയാണ്. ഞാൻ അത് ഡെറിവ് ചെയ്യുന്നില്ല കാരണം ഇതെല്ലാം സെയിം ആണ്, പ്രീവിയസ് പ്രോബ്ലം പോലെ തന്നെ, പ്രീവിയസ് ഡെറിവേഷൻ പോലെ തന്നെയാണ്. Finally we got this value. Again we got t by j is equal to tau by r equal to, here we have capital R, it is not small r, is equal to g theta by L. There is no change in the equation, only change is r. But there is a change for j. J is equal to here pi d raised to 4 by minus small d raised to 4 by 32. That is the only difference. So when we compare the solid shaft and the hollow shaft, this is at a small distance r, this is capital R, this is small r. The difference is here in the case of hollow shaft, this is the equation. For the case of solid shaft, this is the equation. Tau by j is equal to t by j is equal to tau by small r equal to g theta by L. Okay, capital R here because this is the R. Here we use small r. That is the only difference. And one more difference is j value. J value is the main difference. Here in the hollow shaft, this is the j value. In case of solid shaft, j value is equal to pi. Corresponding to this R, we have capital D, d raised to 4 by 32. That is the only difference.
Sir, R tau by r la r എന്ന് പറയുമ്പോൾ
R എന്ന് പറഞ്ഞാൽ ഏതെങ്കിലും എലമെന്റിലേക്കുള്ള ഡിസ്റ്റൻസ് ആണ്. ഓക്കെ, അത് വേരി ചെയ്യാം, അത് വേരി ചെയ്യാം.
രണ്ട് ഈക്വൽ അല്ലേ അപ്പുറത്തെ?
രണ്ട് ഈക്വൽ ആണ്. അതെ 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 അതെ. ബോത്ത് ഇവിടെ ഞാൻ രണ്ടും സ്മോൾ ആറും ക്യാപിറ്റൽ ആർ യൂസ് ചെയ്തിട്ടുണ്ടെങ്കിലും this r and capital R is the distance from center to element where tau is calculating. Okay, അതിലേക്കുള്ള ഡിസ്റ്റൻസ് ആണ് രണ്ട് കേസിൽ. അപ്പൊ ഈ എലമെന്റ് യൂസ് ചെയ്യുന്ന ഇവിടുത്തെ ടോയ കാൽക്കുലേറ്റ് ചെയ്യുന്നത് ദിസ് ഈസ് സ്മോൾ ആർ. ഈ എലമെന്റിലേക്കുള്ള ഡിസ്റ്റൻസ് ആണ് കാൽക്കുലേറ്റ് ചെയ്യുന്നതെങ്കിൽ ദിസ് ഈസ് ക്യാപിറ്റൽ ആർ, സെൻട്രൽ നിന്നുള്ള ദിസ് ഈസ് ക്യാപിറ്റൽ ആർ. ബട്ട് ദ മെയിൻ ഡിഫറൻസ് ഈസ് ദിസ് ജെ വാല്യൂ. ജെ വാല്യൂ വിൽ വേരി. So here in the hollow shaft, j is equal to outer diameter raised to 4 minus inner diameter raised to 4 by 32 into pi. In case of solid shaft, this is equal to pi. This is equal to the outer diameter, the whole outer diameter raised to 4 by 32. That is the only difference. Okay. Any doubt? So we derive the equation and this is the distribution for solid shaft. Then what is the distribution for hollow shaft? For a solid shaft, this is the distribution of tau. At the center, the tau value equal to 0, because we know at the center r equal to 0, then tau is also will be 0. At the surface, r is maximum, tau also maximum. So this is the distribution of shear stress. This is the distribution of shear stress for a solid shaft. What is the distribution for a hollow shaft? What is the distribution for a hollow shaft? Central region shear stress in the distribution. It will be 0. It will be 0 because there is no material there. There is no material in that area. In this area, there is no material. So there is no shear stress distribution there. But the shear stress distribution starts from this point. From this point. And what about the distribution? Here it is 0 or a particular value. Is it a 0 or particular value? It will be value because here from this equation, this is for a hollow shaft. This r is the distance from the center to a point. Okay, so here this in this point, this r is not 0. This r is not 0 in this point. It will be a value. There will be a value here. This value. So this r is not 0 at this point. So there will be a tau value here. So this is the tau value. Then again, tau value increase from that value to maximum value. So this is the distribution in case of a hollow shaft. In case of hollow shaft, this is the distribution. In case of solid shaft, this is the distribution. And similar to the previous last lecture, this is very important. Which one has higher strength? Solid shaft or hollow shaft? Here from this equation we can see, from the distribution we can see, in this region the shear stress is very small. Okay, so we can take the material from this area and distribute the same material in the surface area where shear stress is maximum. So that is hollow shaft. Okay, we take the material from the center region, this changes to hollow, and to maintain the same weight for solid as well as hollow shaft, what we do, we take the material from the center portion and we distribute the material into the surface area where shear stress is maximum. So we got a hollow shaft. So hollow shaft, where is the location of maximum shear stress? The surface area. Okay. Surface area. So in the surface area, actually what we do, we take some material from the center and distribute it in the surface. Okay. So if we distribute some material in the surface area, then of course this value, for example, without this distribution, maybe the shear stress is equal to 10 Pascal. By the distribution of material from the center to the surface, this shear stress value may reduce from 10 to 8 because more material is available to resist this shear stress. Okay, so the shear stress of course will reduce. So we can say the shear stress developed may be less than the allowable shear stress. So the strength of the material can increase. So hollow shaft is better than solid shaft by this distribution. Okay. Okay. സർഫസിലേക്ക് ഡിസ്റ്റൻസ് കൂടിയാലും അവിടെ മെറ്റീരിയൽ നമ്മൾ അഡീഷണൽ പ്രൊവൈഡ് ചെയ്യണല്ലോ. നമ്മൾ കൂടുതൽ മെറ്റീരിയൽ ഇപ്പൊ അതെ ഒരു പർട്ടിക്കുലർ മെറ്റീരിയൽ ഇത്രയും വലിപ്പമുള്ള ഒരു ഷാഫ്റ്റ് എടുത്തു, ഇത്രയും സൈസ് ഉള്ള ഒരു ഷാഫ്റ്റ് എടുക്കുമ്പോൾ വിച്ച് വൺ ഹാസ് ഹയർ സ്ട്രെങ്ത് ഫോർ ദിസ് ബിക്കോസ് ഇറ്റ് ഹാസ് മോർ ക്രോസ് സെക്ഷൻ ഏരിയ. മോർ ക്രോസ് സെക്ഷൻ ഏരിയ ഉണ്ടാവുമ്പോ എന്താ അഡ്വാൻറ്റേജ്? ഈ ഇക്വേഷൻ നോക്കി, ടി ബൈ ജെ ഇസ് ഈക്വൽ ടു ടോ ബൈ ആർ. ടി ബൈ ജെ ഈക്വൽ ടു ടോ ബൈ ആർ. ഓക്കെ, tau equal to T by J into R. Right. So what are the different reasons for this increase in torque? One reason is T. That is, if we supply more torque, this torque will increase. So, for example, I maintain a constant torque. What are the other factors? One is J, one is R. Okay. So, with respect to increasing J value, what happened to this torque? J increase in the torque. Torque R increase in torque. So if I increase the if we change the or take the material from this portion and distribute it here, okay, R increasing, of course R increasing. At the same time, what happened? This J value also, what happened to this J value? J value also increase. J value also increase. But this J value has a T raised to 4 term, raised to 4. But this has only raised to 1. So R value increasing 4 times I can J value increasing. So the net tau value decreasing. Okay. Any other doubt? Is it okay? And the derivation is okay? Next, we have some assumptions in this. Okay, we have some assumptions. These are the assumptions. For the derivation of this equation, we use some assumption. The first one is the material is homogeneous. What is material is homogeneous? Everywhere the property will be same. Okay, everywhere the property will be same. We already discussed the homogeneity of material in the second module. The material is elastic, obey Hooke's law, and so that means the applied torque and corresponding shear stress develop only within the elastic limit. Okay, yield point cross yield. Okay, so then only this equation is valid. The stress do not exceed the elastic limit. Okay, stress strain graph elastic limit cross yield. Then circular cross section remains circular throughout. That is very important assumption. Okay, circular cross section remains circular. For example, in this case, before the deformation, we have a circular cross section like this. In this cross section, sorry. In this cross section, we have a circular cross section. This is a circular cross section. And after deformation, this is my circular cross section. After deformation. And there is no change in that circular cross section. There is no deformation for that circular cross section. Actually, the circular cross section twisted, but there is no change in the circle. When we take the cross section here as well as here, there is no change in the shape. It is remain as a circular cross section. So that is one of the assumptions we use while deriving this equation, torsion equation. Cross section of the shafts which are plane before twist and remain after plane after twist. There is no change in the. If we cut a plane here, at the same plane can be seen after deformation also. Okay, here we can see when we cut a plane, it will be a plane. There is no change in the deformation of the planar structure of the cross section. Okay, that is another assumptions we used. And next one is, and twisting couple activate in acting in the transverse direction. So we already discussed the twisting couple. This is the twisting couple. this is acting in the transverse direction, not along the longitudinal axis. That means the twisting applies not like this. Twisting applies not like this. That means along the longitudinal axis, there is no twisting couple. Along the longitudinal axis, in this direction, there is no twisting couple. Only the twisting couple is acting in the transverse direction. Okay, that is another assumption. Next assumption, the cross section rotate as if rigid. Every diameter rotate through the same angle. Okay, there is no change in the diameter of the circle after rotation. Cross section remains a circle with the same diameter. And the distance between the cross section do not change, hence the axial strain is absent. That's another assumption. That means after rotation and before rotation, for example, in this case, if you take the distance, for example, the distance between these 2 points is equal to 5 centimeter before rotation. And if you take the same 2 points here, if you take the same points, 2 points here after rotation, this distance also will be 5 centimeter. So before rotation and after rotation, there is no change in the distance between the 2 points. Okay, that is another assumption we use while deriving the equation of torsion.
Shortest path.
Yes.
Shortest path ആണ് ഉദ്ദേശിച്ചത്.
Shortest path. If you take any point, any 2 points on the shaft after rotation and before rotation, there is no distance between the difference in distance between the axial in the axial direction.
Okay.
The axial direction, there is no change in the distance between the 2 points. Okay. So, but the limitation of this equation, P by J is equal to tau by R is equal to G theta by L, it can be only used for circular cross section, and material should be linearly elastic. We cannot use this equation for a anisotropic material. Should be linearly elastic material, should be obey Hooke's law. That is the limitation of this equation. Okay. Another one is polar modulus. Polar modulus. So next we are going to develop some terms from this equation. P by J is equal to tau by R equal to G theta by L. This is our torsion equation. In this torsion equation, T equal to, I am taking this portion. I am taking this portion of this equation. T equal to tau by R into J. Tau by R into J. Okay. And in this, T is equal to tau into J by R. I am taking maximum radius. I am taking maximum radius. That means this R equal to capital R, changes to capital R. This R is the distance from the center to the element, but I am considering element at the surface. Then it will be maximum radius R. Okay. What is our aim? When a shaft subjected to torsion, what is our aim? While designing, our aim is to, across any cross section, this tau value should be less than allowable shear stress of the material. Allowable shear stress of the material. Okay, that is our aim. While designing, this is our aim. Across any cross section of the shaft, the tau value developed should be less than allowable shear stress of the material. What happens if this developed tau is greater than allowable shear stress? What happened to the material? Or what happened to the shaft? The സംഭവിക്കുക ഷാഫ്റ്റിന് yes, it will get sheared and there will be a fracture or failure for the shaft. So ഈ ഷാഫ്റ്റ് ഉണ്ടാക്കുന്ന മെറ്റീരിയലിന്റെ അലൂബിൾ ഷിയർ സ്ട്രെസ്, അതായത് ആ മെറ്റീരിയൽ ഷിയർ ചെയ്യാതിരിക്കാൻ ഷിയർ ചെയ്യുന്ന ഷിയർ സ്ട്രെസ് ആണ് അലൂബിൾ ഷിയർ സ്ട്രെസ് ഓഫ് ദാറ്റ് മെറ്റീരിയൽ. അപ്പൊ ഡെവലപ്പ് ചെയ്യുന്ന ഷിയർ സ്ട്രെസ് ഈ ടോർക്ക് കൊണ്ട് ഡെവലപ്പ് ചെയ്യുന്ന ഷിയർ സ്ട്രെസ് should be less than the allowable shear stress of the material. So our aim is to increase or decrease this toe value. What is our aim? Is it increase or decrease this toe value? Develop either shear stress decrease or increase. It should decrease. It should decrease. So while designing a shaft, our aim is to decrease this toe value for a particular torque transmission. I have to transmit, for example, 10 Newton meter torque. 10 Newton meter torque. Okay, so the T value is constant. That is my, in my application, I have to transmit 10 meter torque. So our aim is to reduce this toe value corresponding to 10 Newton meter. What I should do? How can you reduce this toe value? How can I reduce this toe value? By increasing this J by R value. So for a constant torque, to reduce this toe value, I should increase this J by R. And this J by R is called, so we can say this J by R is called shear modulus. This is called shear modulus. Sorry. Polar modulus is at P. Polar modulus. This is called polar modulus. I am taking two shafts. One shaft with a particle radius R, another shaft with another radius R1, another shaft with the radius R2. Okay. 3 cross section shaft. Strength കൂടുതൽ? Which one has higher strength? With respect to generally polar modulus higher ആയിട്ടുള്ള ഷാഫ്റ്റിനായിരിക്കും അല്ലേ?
അതെ സർ.
With a higher polar modulus has more strength. So this polar modulus, because if the polar modulus is high, for a constant torque, the shear stress will be low. If the shear stress is low, that shaft has more capacity to handle this torque. That means the strength of the shaft is higher. So if the polar modulus directly give the strength of the shaft, if a particular cross section, if the polar modulus is higher, then we can directly say the strength of that cross section also higher. So while designing a shaft, you have to select a cross section with a higher polar modulus. How can we select a shaft with a higher polar modulus? In this J by R term is very important. P is equal to J by R. In both we have J by R is polar moment of inertia by maximum radius. In this both we have the radius term pi d raised to 4 by 32, that is J. R is equal to d by 2. So bottom region has d by 2 term or d. In the numerator also we have d term. So how can we select a particular diameter for the shaft? Because if we increase the diameter, the bottom region also increase, as well as top region also increase. But we have to select a diameter such that the top region has higher value than that of, or the numerator region has higher increase than that of denominator region. Okay, such a shaft has higher ZP, has more strength. So ZP directly gives the strength of the shaft. Any doubt?
സാർ പള്ളി പോകണ്ടായിരുന്നു.
എത്ര മണിക്കാ?
12 മണിക്ക്.
ഒരു 10 minutes കേട്ടോ, ഞാൻ പറയാം. ഒരു പ്രോബ്ലം കൂടി എനിക്കുള്ള ഉണ്ട്. എത്ര പേർക്ക് പള്ളി പോകണം?
ഒരു അഞ്ചാറാളുണ്ടാവും.
എന്നാ കുഴപ്പമില്ല, പൊക്കോ. ഓക്കെ, ഞാൻ ഒരു പ്രോബ്ലം ചെയ്തിട്ട് സ്റ്റോപ്പ് ചെയ്യാം. So this is the important time, polar modulus, which gives the strength of the shaft cross section. Another one, a shaft, in the shaft problem, we commonly use power type. What is the relation between power and torque? What is the relation between power and torque for the design of shaft? Power is equal to, power is equal to 2 pi nt by 60. This is the relation between power and torque. That means for a shaft which used to transmit a p amount of power, and the shaft is rotating with the n rpm, that is rotation per minute, then corresponding torque transmitted for the power transmission with the n rpm, the corresponding torque transmitted will be t. So this is the relationship between power and the torque. So if we know the power, directly we can calculate the torque. Another relation you may have, this power is equal to t omega, where omega is equal to
2 pi nu.
2 pi n by 60. 2 pi n by 60. Okay, so you already studied this. So the power, the unit of power is equal to watt. The unit of torque is equal to Newton meter. Force into perpendicular distance. So Newton meter is a unit of this torque. Okay. So if the power is in watt, this torque is in Newton meter. Okay. And for the design of hollow shaft and as well as solid shaft, we can use this equation: T by J is equal to tau by R. Here in this also, T by J, here J in terms of, for the design of the shaft, we have T by J is equal to tau by R. So T by J is equal to, for a circular shaft, pi d raised to 4 by 32 is equal to tau by R equal to maximum. For in case of maximum, that means at the surface. If we consider element at the surface, then R equal to d by 2. Okay, there is not in this term, this d is the cross sectional diameter. It is not vary with respect to the element, with respect to the positional element. It is constant, but this R is vary with respect to the element position. If we consider the element at the surface, then this R equal to diameter by 2, diameter of the cross section by 2. From this we can write T equal to pi by 16 into tau into dq. This is another formula. You should study this formula. This is the formula. This is the formula derived from this formula by substituting all the values. This formula can be only used to calculate the surface shear stress. But commonly we calculate the surface shear stress because this is the area where maximum shear stress is acting. Okay. So next we will do one problem. Okay. So നിങ്ങൾക്ക് ഇത് ഇട്ടിട്ടുണ്ടായില്ലേ? മെറ്റീരിയൽ ഇട്ടിട്ടുണ്ടായില്ല അല്ലേ? Just a second. So here in this, problem, this is a problem where a solid shaft, solid bar having circular cross section with a diameter 40 mm is given, length is given 1.5 meter, subject to the external torque of 375 Newton meter. What is the maximum shear stress in the bar? Calculated top. Maximum shear stress means the shear stress acting on the surface. Where R is maximum, then shear stress is also maximum. So maximum shear stress in the bar is the question. And what is the angular twist also at the ends? And modulus of rigidity is given. Okay, that is the first part of the question. So here in this, tau maximum is the question. So corresponding radius will be the radius of the shaft. Okay, the distance from the center to the outer surface will be the radius, R. Okay, so the R will be the distance from the center. So take the first part of the equation. We have all the data. Submit, and we can calculate the tau max. And second part of the question is to calculate the angular twist, okay, between the ends. For that, take the second part. That is T by J is equal to G theta by L. Here the only unknown is theta. Okay, so we can calculate the theta, and the theta will be in radians. That is very important. In T by J is equal to tau by R equal to G theta by L, the theta should be in radians. Okay, maybe in your question, the theta may be given in terms of degree. So you have to convert into radians while substituting in this equation. Okay, so how can we convert radian and a degree? For a quantity in a radian, multiply with the pi by 180 by pi in order to convert radian into degree. For the conversion from degree to radian, multiply with pi by 180. In the sorry. എന്താ പറ്റി പ്രസന്റ് എത്ര നേരം പറഞ്ഞ വെറുതെ ഇല്ലേ എത്ര കട്ടായി പോയി ഇവിടെ പ്രസന്റ് അല്ലേ ഒരു ക്ലാസ് പ്രസന്റ് അല്ലേ okay so here in this problem can you see okay so in this problem we have all data. The two questions are what is the maximum shear stress and what is the angular twist at the ends. These are the two questions. And to calculate the maximum shear stress will be at the surface. Okay, so we have to submit in this equation. This is the first part which can be used to calculate the maximum shear stress. Here, T by J is equal to tau maximum by R. So if tau changes to tau maximum, then this R, the distance from the center to the element, R is shifted to radius. Okay, so by substituting all the data, we can calculate the tau max, where R is the radius of the shaft. So we can calculate that. To calculate the angular twist, second question is to calculate the angular twist. For calculating the angular twist, we use the second part. That means T by J is equal to G theta by L. Okay, T by J is equal to G theta by L. So from this theta is equal to TL by GJ, can substitute all the data is given, use the same unit, either Newton meter, either in meter or mm, use the same unit for all the quantities. Then we got this in radians. Okay, to convert a radians quantity into degree, multiply with the pi by 1, sorry, 180 by pi. Now to convert a degree quantity into radian, because in some question you may ask to substitute theta in this equation. The theta is given in degree terms. For example, 10 degree, 1 degree twist. So we have to submit or convert that 1 degree into radian. For that, what we do? To convert degree into radian, multiply with the pi by 180. Okay, so 1 into pi by 180, that quantity has to submit in this equation. Because in this equation, this theta is in radian. This is very important. And another question is, so that is we calculate the corresponding angular twist also. Another second part of the question is, if the allowable shear stress is 50 megapascal and allowable angular twist is 2.5 degrees Celsius, sorry, 2.5 degree, what is the maximum permissible torque? That is very important question. Allowable shear stress is, here in this question, it is given allowable shear stress is 50 megapascal. Allowable angular twist is how much? Allowable angular twist is 2.5 degrees degree. Then what is the corresponding torque? So for a shaft, and it has a material with the allowable shear stress of 50 megapascal and allowable angular twist. If the angular twist is greater than 2.5 degree, then we can consider that is a shaft failure. Okay, so allowable angular twist is 2.5 degree. Then what is the maximum torque I can transmit through this shaft? This is the question. For that, we can use this equation. T by J equal to tau by R equal to G theta by L. Okay. For this, we have to calculate the tau, T value. So in this, for calculating the T, we have two equations. T by J is equal to tau by R is the first equation. Another equation, T by J is equal to G theta by L. We have two equations for calculating this T value. Okay. So what we do? We calculate T value for both cases. So by substituting this tau equal to 50 megapascal, we calculate the T value. So if I substitute 50 megapascal, what will be the R? What will be the R? R will be the radius, because here the allowable shear stress is 50 megapascal. That means that will be at the surface. That is the maximum shear stress area. So the distance from the center to that surface, this will be R, radius of the shaft. Okay, so in this problem, the radius will be shaft R. And again, by substituting 2.5 degree here, first we have to convert this 2.5 into radians. For that, you have to multiply with a pi by 180 degree. Then substitute this theta here. All other data are given. We got T value, T1 value from this equation, T2 value from this equation. We got two T value. Two torque values is available from these two equations. Which one I select? I got T2 T value. Which one I select from these two? Higher T value or lower T value? Higher T value.
Lower.
Yes, lower T value is selected. What is the reason for that? If I select, yes, if I select the higher T value, For example, in this problem, we got two t value. What are they? In this problem, we got two t value, that is 681. 681 and 731. These are the two t value. If I select 731, what will happen? If we substitute that 731 here, corresponding shear stress will be greater than 50. Will be greater than 50 because corresponding to 50 megapascal shear stress, the T value is 628. And if the T value is greater than 628, then correspondingly this tau value also increase above that of 50. Then the shaft will fail because of the shear failure. So, but if we select 628 and if we substitute the 628 here in this equation, corresponding theta value will be less than 2.5. 2.5 is the allowable limit. It will be less than 2.5. That is permissible. So we have to select the lower value, that is 628. Okay. So that is a problem. So you have to do this problem based on two conditions, calculate the t value. Okay. Similarly, we have another problems. Please do these problems. And similarly, this is another problem with the power is given in this problem. In this problem, power is given. Power and RPM is given. So first, you should convert into. So here we can see the 1 degree is converted into radian by multiplying with the pi by 180. So here in this problem, power is given. Convert power into torque by using this equation P is equal to 2 by nt by 60. Okay, so we got T. From this we can calculate the diameter. And what about the diameter? What about the diameter? For example, in this question, based on allowable shear stress condition as well as angular twist condition, T is given, external torque is given. The question is asking about D. What is the diameter? So in this two condition, we got two diameter. For the allowable torque condition, we got diameter D1. For the allowable twist, we got another diameter D2. Which one I select? Lower or higher? And this one? Higher D value is selected. In case of diameter, we have to select the higher D value because with respect to increasing the size of the cross section, the strength also increase. Okay, so if we select any lower D value, one of the condition will not satisfy. So in case of diameter, we have to select the higher diameter. In case of torque, we have to select the lower torque. Okay. So in this problem, we got two diameter. That is, first one is 64.6 and 89.2, where 89.2 satisfy two conditions. You can substitute this 89.2 in this two equation. Then you can check whether the allowable criteria are satisfied or not. Okay, if we submit 89, then allowable condition will satisfy. But if we substitute 64, then one of the allowable condition will not satisfy. Okay, so this is very important. While selecting the diameter from the two conditions, select the diameter with the higher value. But when we select the torque from the two conditions, select the torque with the lower value. Okay, so that is about the problems. And I will give a tutorial based on this torsion. So in the exam also you have to study this tutorial. Sorry. This is the tutorial based on the torsion. See here in this, there are different types of questions are there based on torsion. This is the first question. The solid shaft, circular shaft subjected to internal torque 5 kilonewton. Determine the shear stress developed at a point A and B. A and B. So at this point A, the radius is equal to 40. At point B, the radius is R equal to 30. Because this R is the distance from the center to the element we are considering. So here in this point A, this is the element at the surface. At point B, this is the element that is at a 30 distance from the center. So the R value will be radius. Based on, by varying the R value, we can calculate the shear stress at point A and B. Here we can see shear stress at A is equal to 49 at surface. At B, it is 37. So at B, it is less. And this is the elemental representation. It may ask how this element is represented. It is from Hibbeler. So another question is this one. A shaft is hollow from A to B. A to B is hollow. B to C, it is solid shaft. Determine the maximum shear stress developed in the shaft. Outer diameter is given. Thickness of the wall is given. Here the thickness is given. Okay. This question is to calculate the maximum shear stress developed. Okay. That is the question. And here in this problem, again, one more thing. There are two torque is acting. A 2 kilonewton is acting here. Here a 4 kilonewton is acting. Okay. So in this problem, we have to use what you study in beams. You have studied in about a section. How can we calculate the shear force at a section? By using a section method. So here in this problem, two kilonewton is acting. Okay, so here in this problem, this is the problem. 2 kilonewton acting here, 4 kilonewton acting here. Okay, so this is ABC. ABC. So this is ABC. Okay. So here also we use the concept of sections. What is the distribution of torque here? If we consider the section here, a section here, to the right of the section, we have only 2 kilonewton. Okay. So that means at this point it is 0. It is increased to 2 kilonewton here. And if we consider section anywhere in this area between B and C, this 2 kilonewton will not vary. So it is up to this point, it is 2 kilonewton. And if we consider another section in between A and B, here, to the right of the section, we have 4 that is acting clockwise and 2 which is acting again clockwise. So both we can add 4 plus 2, 6. So at this section, we have 6 kilonewton. 6 kilonewton. And if we consider the section here, it will be 6 kilonewton. If it is here, it will be 6 kilonewton. So everywhere it is 6 kilonewton. So in this point, it is vary from 2 kilonewton to 6 kilonewton. And at this point, this is fixed end. There will be a reaction of 4 plus 2, 6 in the opposite direction. That means it will reduce to 0 at this point. So this is the distribution of torque. This is the distribution of torque. So when we calculate anything in this area, we have to use torque is equal to 2 kilonewton. Okay. And anything you calculate in this AB area, you have to use T is equal to 6 kilonewton. This is very important. Okay. So here we can see. So when a shaft subjected to more than one type of torque, first you have to draw this type of torque distribution. Then In the CB area, use 6 kilonewton. The AB area torque T equal to 2 kilonewton. Okay. So I explain all these things here. Okay, 6 kilonewton is here and 4 kilonewton. At a point C, it is equal to 0. So for calculating the polar moment of it at AB, we calculate it. For BC area also we calculate it. And we use separate formula for calculating the shear stress at AB and shear stress at BC. For this area, AB area, T value should give as AB area, it will be 2. It will be 2. But in BC area, T value for the calculation is equal to 6. So we got 2 separate answers. Okay. Same way, here also we can draw the distribution of shear stress. Any doubt? What about here in this problem? In this problem, this is the distribution. Okay. So here in this, at this point, we have 4 kilonewton, which is clockwise. So clockwise 4 kilonewton. We got clockwise 4 kilonewton. And in between there is no variation. Okay, so it is constant. In between it is constant. But at this point we can see, 4 kilonewton, it is clockwise, but here it is anti-clockwise. 10 kilonewton is anti-clockwise. So here we are not increasing 10 kilonewton, but decreasing 10 kilonewton. Decreasing 10 kilonewton because the direction of rotation is different. So this is 10 kilonewton. Okay. Then in between there is no variation. This is, and this reaches to 0. So when we mark, this is 4 kilonewton. And here also 4 kilonewton, but it is reduced by amount of 10 kilonewton, then this will be equal to 6 kilonewton. Here also it will be 6 kilonewton, here it will be 0. So when we draw or calculating anything in this area, AC area, use 6 kilonewton as torque is equal to 6 kilonewton. Torque is equal to 6 kilonewton. For calculating or applying T by J is equal to dou by R, T will be 6 kilonewton. But in this area, we have T equal to 4 kilonewton. Get the doubt undo ninga? No. അങ്ങനെ കുഴപ്പം ഇപ്പൊ 4 ഉം 6 ഉം കിട്ടിയില്ലേ 6 ആക്ച്വലി -6 കിട്ടിയേ നിങ്ങൾക്ക് 6 ആക്ച്വലി -6 കിട്ടിയേ 4 + 4 കിട്ടിയേ പക്ഷെ അത് രണ്ടും പ്ലസ് തന്നെ എടുത്താൽ മതി ഡയറക്ഷൻ നമുക്ക് ഇമ്പോർട്ടന്റ് ഇല്ല ടോർക്ക് കാൽക്കുലേറ്റ് ചെയ്യുമ്പോൾ ആ ടി എന്ന് പറയുന്നത് പോസിറ്റീവ് ആയിട്ട് തന്നെ കൊടുത്താൽ മതി അപ്പൊ നിങ്ങൾക്ക് ക്ലോക്ക് വൈസോ ആന്റി ക്ലോക്ക് വൈസോ എന്തും പോസിറ്റീവ് ആയിട്ട് എടുക്കാം ബട്ട് ഇങ്ങനെ ഓപ്പോസിറ്റ് ഡയറക്ഷൻ വരുമ്പോൾ എന്ത് ചെയ്യണം ഇപ്പൊ ഫോർ എക്സാമ്പിൾ ഇതിപ്പോ സെയിം ഡയറക്ഷൻ ആയിരുന്നെങ്കിൽ ഞാൻ കാണിച്ചു തരാം അതായത് രണ്ടും സെയിം ഡയറക്ഷൻ ആണെങ്കിൽ എങ്ങനെയാന്ന് കാണിച്ചു തരാം സെയിം ഡയറക്ഷൻ ആയിരുന്നെങ്കിൽ ഇങ്ങനെ വരും അതായത് സെയിം ഡയറക്ഷൻ ആണെങ്കിൽ ആദ്യം ഇത് 4 ഈ ഏരിയയിൽ ഒന്നുമില്ല അതുകൊണ്ട് 4 ഇവിടെ 10 കിലോന്യൂട്ടൺ ഇത് ക്ലോക്ക് വൈസ് ഇതും ക്ലോക്ക് വൈസ് ആയിരുന്നെങ്കിൽ അഗൈൻ ഇത് 10 ന്യൂട്ടൺ ഇൻക്രീസ് ചെയ്യും 10 ന്യൂട്ടൺ മീറ്റർ എന്നിട്ട് ഇത് ഇങ്ങനെയാവും അപ്പൊ ഇവിടുത്തെ വാല്യൂ എന്താ ഇത് 4 ഇത് 4 ഇത് 10 + 4 14 വരുമായിരുന്നു രണ്ടും സെയിം ഡയറക്ഷൻ ആണ് ഇത് ഓപ്പോസിറ്റ് ഡയറക്ഷൻ ആയതുകൊണ്ട് എന്ത് ചെയ്യും ഇതിന്റെ 4 കഴിഞ്ഞിട്ട് ഓപ്പോസിറ്റ് ഡയറക്ഷൻ ആയതുകൊണ്ട് തിരിച്ചും കൂടെ 6 കിലോ 10 വരുമ്പോ ഇവിടെ 6 ആവും ഓക്കെ അതുപോലെ നിങ്ങൾ ഇത് ഡ്രോ ചെയ്യണം ഇതുണ്ടോ ഈ കേസ് നോക്കി ഈ കേസിൽ വരുമ്പോ ഇവിടെ 400 ആണ് 400 അതുകൊണ്ട് ഞാൻ 400 ഇൻക്രീസ് ചെയ്തു ഓക്കെ ഈ റീജിയനിലൊന്നുമില്ല അതുകൊണ്ട് 400 കോൺസ്റ്റന്റ് ആയിട്ട് വെച്ചു ഈ പോയിന്റിൽ എന്താ വന്നേ ഓപ്പോസിറ്റ് ഡയറക്ഷനിൽ 200 വന്നു ഈ 400 ഞാൻ എടുത്ത ഡയറക്ഷൻ ഓപ്പോസിറ്റ് ഡയറക്ഷൻ, അതുകൊണ്ട് ഇത് -200 വന്നു. അപ്പൊ 400 - 200 അഗൈൻ 200 ആയി, കോൺസ്റ്റന്റ് വന്നു ഇവിടെ വരെയും. ഇവിടെ 500 വന്നു, എന്താ ഡയറക്ഷൻ? അഗൈൻ ഈ 400ന്റെ ഓപ്പോസിറ്റ് ഡയറക്ഷനാണ്, അതായത് വീണ്ടും താഴോട്ട് വേണം. സോ അഗൈൻ 500 താഴോട്ട് പോയി. ഹിയർ ഇറ്റ് ഈസ് 200, 500 താഴോട്ട് പോകുമ്പോൾ ഇറ്റ് ഈസ് -300. So again it is -300, and the reaction is the algebraic sum of all the torque. It will reach 0. Similar to your shear force diagram, ഇത് 0 അവസാനിക്കുള്ളൂ. Okay, but നിങ്ങൾ ഈ ഏരിയയിലെ 0 to C ഈ ഏരിയയിലെ ടോർക്ക് എടുക്കുമ്പോൾ നിങ്ങൾ -300 എടുക്കരുത്, 300 തന്നെ എടുക്കുക. നമ്മൾ ജസ്റ്റ് ഡയറക്ഷൻ ആണ് ഈ മൈനസ് കൊണ്ട് റെപ്രസെന്റ് ചെയ്യുന്നത്, അത് ഇറലവന്റ് ആണ്. Here we have 200, here in this area we have 400. Okay, നിങ്ങൾക്ക് ഈ സോൾവ് ക്വസ്റ്റ്യൻ തരാം, അല്ലെ സോൾവ് ട്യൂട്ടോറിയൽ തരാം. സോ ഇറ്റ് വിൽ ബി ക്ലിയർ മോർ. So similarly, and this is another problem. This also can be solved based on the same concept. This is another problem. Okay, this is very simple. The problem is very simple. We just use this equation, d by j is equal to tau by r. Okay, this is the problem which is similar to the problem which we are did. The torque is calculated, then the angular twist also calculated, and the difference between solid shaft and hollow shaft, another problem. And this problem is not recurred. This is actually a statically indeterminate problem. 18th problem is not recurred. As per your syllabus, the statically indeterminate problem is not included. So this 18th problem is not recurred for, but you can do this problem. Okay. So this is about the torsion problems. This is very simple problem. Any doubt? This is about torsion. Okay, so there are different varieties of problem you can see from Hibbeler textbook. This problem is taken from Hibbeler. Okay, so what is the shear stress developed in the material at the inner and outer wall of the center portion? This is the question. Here, what is the shear stress developed? So when I apply 80 kilonewton, corresponding torque is equal to 80 into 500. So torque applied T is equal to 80 into 500. So then simply it is T by J is equal to tau by R. We can calculate the tau value. So here in this problem, only difficulty, or you have to understand this 80 and 500 is the torque. Okay, that is the only difference. And here the same problem what we did. Okay. Any other doubt? Any other doubt? So നിങ്ങൾ just notes വായിച്ചു നോക്കുക, then textbook നോക്കുക, and if you have any doubt you can ask, but this portion will be in your series exam. Okay, there will be a problem, and maybe this derivation also for this series exam. Okay. Any doubt? Second module means which one? Second module. അത് കഴിഞ്ഞ എക്സാമിന് ഇട്ടില്ലായിരുന്നു അല്ലെ? ഞാൻ നോക്കട്ടെ. ലാസ്റ്റ് എക്സാം കഴിഞ്ഞിട്ടുള്ള ബാക്കി എല്ലാ ടോപ്പിക്സും ഉണ്ടാവും. Yes. That means second module and third module. Second and third. Second module that is stress strain relationship, Hooke's law, the different elastic constants, thermostress, thermostrain, then torsion area, then moment. ഇത്രയും പോർഷൻ ഉണ്ടാവും. ഇവിടെ മുതലില്ല, ഇവിടെ മുതൽ സാറ് പഠിപ്പിച്ചല്ല, ഇവിടെ മുതലുണ്ടാവും. ഇത്രയും ഏരിയ ഉണ്ടാവും കേട്ടോ. സെക്കൻഡ് മോഡ്യൂൾ ആയതുകൊണ്ട് തേർഡ് മോഡ്യൂളിന്റെ ഇത്രയും പോർഷൻസ്. ഓക്കെ, അപ്പൊ നീറ്റായിട്ട് പഠിക്കുക. ആയിപ്പോയോ പ്രോബ്ലം